Hello everyone. Now I'm going to talk about the Poljak Rodl function again. This is second part. So the function is defined as Fn equals the minimum of the chromatic number of the product graph, where this chromatic number of both G and H is at least n. Okay. So this is the Poljak Rodl function. We have proved that Fn is greater or equal to half n plus an arrow term. This is of small order, lower order arrow term. Okay, so this is this is less or equal to. This is less. So this is an upper bound. This is an upper bound. But today we're going to talk about what is an lower bound. Well, basically, there's no good lower bound. We know that f4 equals 4. Because this function is monotone, so this implies that for every n greater or equal to 4, fn is greater or equal to 4. This is the best we know about this lower bound. So we don't know if there's any n such that fn is greater or equal to 5. It's very tricky situation. So, but now today we're going to prove that so Fn could be bounded by a constant. We're going to prove the following theorem. The theorem is by Poljak Rodl. That's why it's called a Poljak Rodl function. And also, there's one part is attributed to Schiller. That is the if Fn is bounded by a constant, if Fn is less or equal to c for some constant c, then the bound is bounded by a small number, 9. So it's bounded, if it's bounded by a constant, it's bounded by a small constant. So we're going to prove this theorem. So to prove this theorem, we need to go to the product of directed graphs. So suppose D1, D2, D1, D2, these are digraphs, directed graphs. And for direct graphs, the edges, their orientations, but we not allow diagonals. So between two vertices, we could have opposite arcs, or just one arc is allowed. So we could have opposite arcs or single arcs. Then we define the product of digraphs. So D1, D2, D1 times D2. We just define the arc set, the arcs. So what are the arcs of the? We say the vertices are pairs, x, y, such that x is the vertex of x, d1, and y is the vertex of d2. And in which x, y, there's a direct arc from x, y to x prime, y prime, if and only if there's an arc from x to x prime, this is in d1, and from y to y prime, this is in d2. This is in D2. So let's compare the with the product of undirected graphs. Undirected graphs is that if you have an edge here, you take the product, and the vertices are the coordinates, the pairs of the vertices. So there are 4 vertices in the product, and the edges is like this, right? So if both coordinates are adjacent, then the pair is adjacent to that pair. And if it's a directed graph, so if you like a directed edge, there's a directed edge. If you take the product of this directed edge, there's an arc from the source to the sink. This source has to both coordinates is a source, and both coordinates is sink. So there's an arc going from here to here. There's no arc between this pair of vertices. And if you Okay, this, if you reverse the direction of this arc, then you get an arc from here to here. Okay, so that's the product of directed graphs. So we'll use this is directed graph, and this one is the underlying graph. This is the underlying graph. So it's the undirected graph obtained from D by forgetting or omitting the orientations. So each directed edge become an undirected edge. It follows from this definition. You can say let's use D inverse. This is a directed graph obtained by like reversing the direction of all the edges obtained from D by reversing the directions of all the edges of all the arcs. In D. Okay. So then you can say from this picture, it's say if you take D1, it's a directed graph, but I take the underlying graph, so this became an undirected graph, and then multiply D2. So this is the product of two undirected graphs, and this is actually equal to, you take D1 times D2. So this is the product of two directed graphs, and then take the underlying graph. Say, forget about the orientation of the arcs, but then there's another one that's the union of D1 times D2 to the inverse, and take the underlying graph. So just like this. So this is the product of underlying graph of these two arcs. You got this. And you first take the product of D1 times D2, and then take D1 times the inverse of D2. Then you get all the edges back to the undirected graph. So I'm writing this equality here. So I treat this as a set of edges. This is an edges set. It's a set. It's a graph, and it's also treated as an edges set. So this set of edges is union of this edges set and this edges set. Okay. So now from this we have this inequality that the Cramér number, the Cramér number of the product, the Cramér number of the product of two undirected graphs. This is Cramér number of undirected graphs. So this is less or equal to the Cramér number of D1 times D2 and times the Cramér number of D1 times D2 inverse. Okay. So when I talk about the Cramér number, so this is defined. The Cramér number of the directed graph is simply the Cramér number of the underlying graph. So this coloring of a directed graph is just if there's an arc between one vertex to another, they should get distinct colors. So that's the same thing as an edge between them. So so this is the product of undirected graph. This is related to the Cramér number product of directed graphs. So we define a Poljak Rodl function for the directed graphs. So there's a relation between that. So we define, that's called definition. So we use Gn, this is another function, it's also Poljak Rodl functions, the minimum of the Cramér number D1 times D2, and the Cramér number of both D1 and D2 is greater or equal to n. So this is the Poljak Rodl function for directed graphs. And we define another function, which is Hn, which is the minimum of the maximum of the Cramér number of D1 times d2, and the chromatic number of d1 times d2 inverse the maximum taken among all those graphs d1, d2, which has chromatic number at least n. Okay? So this is definition of Hn. It follows from the definition that Gn is bounded from above by Hn, and this is bounded by Fn. This is for the product of undirected graphs. But from here, so you take the product of any two graphs, undirected graphs, you can put annotations there so it becomes directed. And then this is from here, you can say that this is that's why equal to Hn squared. So if Fn is bounded, then all this Gn and Hn are bounded. Okay. So the theorem we're going to prove is that if Fn is bounded by constant, then it's bounded by 9. And this follows from the following theorem. The theorem says that if Gn is bounded, if Gn is less or equal to C for some C, then Gn is bounded by 3, less or equal to 3. So if it either goes to infinity, when n goes to infinity, or it's bounded by 3. And the same thing is true for this Hn. If Hn is bounded by some constant, then it's bounded by 3. So this is, then Hn is bounded by 3. Okay? So the theorem we want to prove is that if Fn is bounded, then it's bounded by 9. And it follows from this theorem, right? If Fn is bounded, then Hn is bounded. Hn is bounded, and Hn is bounded by 3. And therefore Fn is bounded by the square of 3, which is 9. So what we need to do is to prove this theorem. Okay. To prove this theorem, we need to define something like the line graph of a directed graph. So, these are directed graph. This is a digraph. This is the partial, the partial D, something like the line graph of this directed graph. Okay, the vertices are arcs of these graphs. Vertices of this graph is the same thing as the arc set of D. Okay. And when is two arcs, there's an arc directed edge from one arc to another. That is if and only if they are consecutive arcs in D. So let's write take an arc. So this is xy is an arc. Xy is an arc. Okay, in AD. So this is directed. There's a directed edge from xy to x prime y prime. So xy prime. So xy is an arc of D, and x prime y prime is also an arc of D. So they are vertices of this partial D, and there's an arc from xy to x prime y prime if and only if y equals x prime. So consecutive arcs form an arc. So this is an arc. This is an arc in D, which is a vertex of partial D, and this is another arc in this direction in D, and then so these are two vertices of the line graph, and then there's an arc from this vertex to this vertex. That's the definition of this partial D. And so first we'll show a relation between the chromatic number of this graph and the chromatic number of this graph. Okay. So let's put a lemma here. The first lemma is that if the chromatic number of D is less or equal to something like K to K over 2, say floor. If the chromatic number of D is bounded by this number, then the chromatic number of this line graph is bounded by K. And another one is the bound of this. So on the other hand, if the chromatic number of this graph is bounded by K, then the chromatic number of this graph is bounded by 2 to the K. Okay? So you can say the converse if so usually actually we're using the converse. So if this is bigger than K, if the chromatic number of this one is bigger than K and the chromatic of this one is bigger than this number. Okay, so let's first prove this lemma. So first one, I take a coloring of this directed graph by colors from this set. So using say phi is from the vertices of D to this set I use this one, say K over 2. I use this one to denote all this set of half K subsets of K. Right? So this is a set of K colors, and this is by using each vertex is colored by a half K over 2 subset of this set. Right? So it's a proper coloring. So if this is a proper coloring of this graph, then if this is a proper coloring of D, then I can define the coloring of this line graph by K colors as follows. Then for any arc xy of D that we define coloring, so let's call it capital Phi. This is color this xy, this arc. Right? This is any color is an arbitrary color, is an arbitrary color. It's an arbitrary color in the difference of these two sets. Let's write it here. It's an arbitrary color in phi y minus phi x. Okay, so because phi colors vertices by K over 2 subsets, so phi x is a set of this size, and phi y is also a set of this size, and they are distinct. Because they are adjacent, so they are colored by distinct subsets. Therefore, this set is not empty. So you can find the color from here. Then I assign this color to this arc. Now you can say that if you have an arc, say this is an arc, this is x, y, and this is y to z. So these two arcs, they are adjacent in the partial D. But the color of this one is in y but not in D. So this is in z but not in y. So they cannot be the same color, right? Because So this is alpha, and this is color beta. Beta is in Y, alpha is in Y, but beta is not in Y. So they cannot be same color. So this is a proper coloring of this partial graph. This proves this part. Proves this part. Now conversely, sorry, not conversely, the next one. The next one, so if we have a coloring of the partial D with K colors, so let's say this is the coloring of this line graph with K colors, the vertices of this graph to K colors, right? Using K colors. It's a proper color. It's a proper color. As shown, this is a proper color. Then I can color the vertices of D by this by another color. So that 5V. So for each vertex V, the 5V be this set, be this set of phi E, where E is outgoing arc. Say that's right. This is outgoing arc of V. Okay. So so for this is for each vertex of D. Okay. So you take a vertex V, and these are the outgoing arcs, and then maybe some incoming arcs, and each arc is assigned a color from this K. So now I color this vertex with the color of this arcs, and certainly this. So if there's an arc from X to Y, so this is X and this is Y, and if this is colored by alpha, and then alpha is in phi X, right? Because it's outgoing of this vertex, and alpha is not in the color of any outgoing arcs of Y, because if Y, this is outgoing arc of Y, then it is not alpha, right? This cannot be alpha, because that's right. So this is not alpha. This is not alpha, because if this is colored by alpha, then this arc and this arc, they are adjacent. There's a direct edge from this one, so they cannot be colored by the same color. So therefore, and this is a proper coloring of this D. And how many colors they use? The colors are subsets of this K set. Therefore, it's at most 2 to the K. The number of colors is 2 to the K colors in this coloring. So this finishes the proof of this lemma. Finish the proof of this lemma. And now let's look at another easy observation. Okay, let's erase this. Okay. So his observation is that so if you look at the product of this graph, so this is 2 digraph, and this is the same thing as the product, the 9 graph of this. So if you take the product of the 9 graphs of 2 directed graphs, is the same thing as take the product of 2 graphs and then take the 9 graph. It's easily verified by this definition. And also, if you take the inverse, that's the same thing. If you take the 9 graph first and then take the inverse. Let's see. Okay, so we're going to prove this. So what we're going to prove? We're going to prove that if Gn is bounded then it's bounded by some constant. It's bounded by 3. If Gn is bounded by constant, then it's bounded by 3. But first we prove things a little bit weaker. So that is, actually this is what proved by Poljak Rodl. So if Gn is less or equal to C for some constant, for some C, then Gn is less or equal to 4 for every n. For every n. This is for every n. Okay? Not for a single n, but for every a. For every n. So I mean, so I didn't write it. So when I say Gn is less or equal to C, that means for every n is less or equal to C. Okay? Not for a particular n. Okay. So we prove this. So we choose this. We assume it's bounded. Assume Gn is bounded. Otherwise, there's nothing to prove. Assume Gn is bounded by a constant, by some C. So we choose this C to be the smallest one. So we choose the smallest bound. Choose the minimum. Choose the smallest bound C. So this is the smallest one, that every Gn is less or equal to C. And because Gn is a monotone, it's non-decreasing. This implies that there exists an n0 such that for every n greater or equal to n0, this Gn is equal to C. Right? So this bound is attained, and it's after some n0 it stays C. Okay, now we let n1 equals 2 to the n0. Then Gn1 is equal to C. So this means what? This means that there exists D1, D2, and the Cramér number of D1, the Cramér number of D2 is greater or equal to N1, and the product has Cramér number equal to C. Okay, let's go. This is why Gn1 equals C. Okay. Now we look at the line graph of this. So the line graph of D1, line graph of D2, they have Cramér number. This implies the Cramér number of the line graph D1 and the Cramér number of line graph D2 is greater or equal to n0, because if, as this is just lemma we proved before, if this is less than n0, if this Cramér number, this is less than that, and then if this is less than n0, then this should be less than 2 to the n0, which is less than n1. Okay? And then because this is greater than that, and therefore the product, so the product of the two graphs, D1 times D2, and this is greater or equal to Gn0, because Gn0 is the minimum among those, the Cramér number of those product with both coordinates, Cramér number of at least n0. But this one is C, so this is also C. So it's greater or equal to C. Now this is greater or equal to C, then this implies that, so okay, this is the same because, so this is the same as D1 times D2, right, because that's the same thing, and this is greater or equal to C, and this implies the Cramér number the Comac number of D1 times D2 is less than the C minus 1, choose half, right? Because by the lemma we proved that if this graph has Comac number, sorry, this is greater than this. By the lemma we proved that if this graph has Comac number less or equal to this number, then its line graph should have Comac number less or equal to C minus 1. Okay, that's what I proved. Because this is big, at least C, and this implies this is bigger than that. But we know the Comac number, we know it is a C. So this Comac number is C. So that means C is greater than C minus 1 and half. And this is true. You can easily, this is a function which grows very fast as function of this C. So this implies, it's easy to verify that this implies C is less or equal to 4. If you plug in C equals 5, this is not true anymore. So that means C is less or equal to 4. So this proves this lemma. And the same argument, you can prove that if Hn is bounded by C for some C, then Hn is bounded by 4. It's bounded by 4. Just apply the same argument to both d times d2 and d times d2 inverse. Okay? And this implies that the Fn, if Fn is bounded, then it's bounded by 16, by the square of 4. So that is Poljak Rodl function. This is Poljak Rodl proved this theorem. Then next I will show you that the minimum cannot be 4, and therefore it's bounded by 3. Okay? So next I'll show you that it cannot be 4. So this I improved that. Okay, so we improve this to 3. We improve this to 3. Okay. So assume this is, assume this is not true. This is not true. Then what it means? We know already. We assume it's bounded, right? But it's not bounded by 3. But we know it's bounded by 4, right? So therefore, this means that the minimum C that is upper bound for all the Gn, that is 4. So this means that there exists n naught such that for every n greater or equal to n naught, this Gn equals 4, right? Because not bounded by 3, but bounded by 4. Okay, now that n1 equals 2 to the n naught and n2 equals 2 to the n1. Because Gn2, so Gn2 is equal to 4, right? This implies that there are two graphs, D1, D2, D1, D2, digraphs. They are digraphs with Comac number with chi d1, chi d2 is great or equal to n2, and their product equals 4. It's 4 color. Now I take the partial of d1, d2, and then by the argument we have already said that this one and we are saying that the chromatic number of this one and the chromatic number of this one is greater or equal to n1. By the number we have shown, because this is the chromatic number is greater or equal to 2 to the n1, then the chromatic number 9 graph is greater or equal to n1. And similarly, if this is, then take the 9 graph this one, so the chromatic number of 9 graph of the 9 graph of d1 and the chromatic of the 9 graph of d2, this is greater to n0, and therefore both direct graph has chromatic that is n0, and the gn0 is 4. gn0 is 4. This means that the chromatic number of the product of these two, d1 times d2, this is greater or equal to 4, right? Because both have chromatic number at least n0, and so their product has chromatic number greater or equal to gn0. gn0 is 4. So, but this is the same thing as we said. You take the 9 graph of the product. It's the same thing as you take the 9 graph of the product graph. The first, okay, let's write it here. So it's the same thing. This is the 9 graph of the 9 graph of d1 times d2. And this is greater or equal to 4. Okay, this is greater or equal to 4. But we know d1 and d2 has chromatic number 4. So this actually means d1 times d2 is homomorphic to k4. Okay. And k4, by k4 here we mean this diagram. So this is my k4. This is my k4, and the vertices of this k4 1, 2, 3, 4, and between every pair, every ij, there's an arc from I to j. So this is a diagram. So there's an arc going this way, and there's also an arc going that way. Okay. So for every distinct ij is an arc. Okay. So if you take two vertices of this, so this coloring is a homomorphism to this directed graph. Okay, so this is homomorphism. That means arc preserving vertex mapping. Okay. And then it is easy to say that if this is homomorphic to this one, and then the product, the line graph is homomorphic to the line graph of K4. Okay? And the line graph of this line graph is homomorphic to the line graph of K4. Okay, what is this graph? So this, we know that the chromatic number of this one is greater or equal to 4. This implies that the chromatic number of this graph is greater or equal to 4. Okay. So to prove that, to get a contradiction, what do we need to do? We need to prove that this graph is actually 3 colorable. Okay? So, but this one is 3 colorable. but this graph is 3 colorable. 3 colorable. That's a contradiction. Okay. So now, how do you show this graph is 3 colorable? Well, when I was doing a PhD degree, I didn't know about this result. And actually, that result was not published at that time. So I find this argument. So I know if this graph is 3 colorable, then you can prove this is bounded by 3. Then how do you prove this graph 3 colorable? You just color it, right? There's not too many vertices in here. You just color it. But there was very nice coloring. So you can color it by brute force. It's not very big. You can draw this graph in a piece of A4 size paper. But there's very nice and easy coloring, which is easy to verify, which is provided by Scheller. So, so how do you color it? So what are the vertices of this? The vertices of this graph, is what? So the vertices of this K4 is 1, 2, 3, 4. So these are the vertices, 1, 2, 3, 4 of this graph. And what are the vertices of this graph? These are arcs. So that means the vertex of this one is ij, where ij belong to 1, 2, 3, 4, and they are distinct. I and j are distinct. And that's the vertices of this graph. And what are the vertices of this graph? This graph, the vertices are the direct adjacent arcs. So it is consecutive arcs of this graph. Right? Each consecutive arc of this graph is an arc of this one, and there's a vertex of this one. So consecutive arc. What is a consecutive arc? That is just triples. This is equal to ijk. The triples, say ijk. They are elements from this 4, and I is different from j. So that means ij is an arc here, and j is not equal to k. So that are the vertices of this graph. So I is maybe equal to k. I is different from j, and j is different from k. So what do we need to do? We need to color the vertices, color those triples by 3 colors, so that adjacent vertices get distinct color. What is adjacent? So ijk is there's directly from ijk to where? So they have to be consecutive arcs. Consecutive means what? Means that this is only to jkl for some l. So that is, these are the arcs of this graph, of this partial K4. So we just make sure that we just need to color the triples that have the property that these two are different, these two are different. Okay? So we want to color triples of this type, so that by 3 colors, so the triple of this type, of this one, is colored by distinct from this one. So how do we color it? I just define this coloring ijk to be j, if j is different from 4. And if j is 4, then I color it by s. Right? If j equals 4, and then s is in any color which is in the 3 color minus ik. Okay, so this is the coloring of the vertices of this graph. Okay, so I look at this triple. If this is not 4, I color it by this color. So it's colored from 1 to 3. Okay, and if this is 4, then 1 to 3, this take away 2 colors. There's at least one color remaining. I just color it by that color. If I equals k, I have two choices. I then arbitrarily choose one. So this is a good current because if you look at this, they get distinct colors. Okay? If this is colored by J, if J is not 4, it's colored by J. And this is why it doesn't matter whether it's K is 4 or not. This is not colored by J. Right? This is colored by J. This is not colored by J. If J is 4, then this is not colored by I or K. And then this K is not 4, so it's colored by K. Therefore, they get distinct color. So this is proper 3 current. So this proves this statement. And therefore, we get a contradiction. The contradiction comes from the assumption that the bound is 4. So that therefore the minimum bound of this function Gn cannot be 4, and therefore it's 3. So this means that if Gn is bounded by some constant, for some constant C, again this means for every n is bounded by C, then Gn is less or equal to 3. Again, the same argument, you just replace this d times d1 by the maximum d1 times d2 and the d1 times the inverse of d2, you get this conclusion. If Hn is bounded by C for some C, then Hn is bounded by 3. Is less or equal to 3. And this implies that if Fn is bounded by constant, then Fn is bounded by 9, the square of 3. Okay, that's the end of this lecture.